Okay, today we're going to find a different way of finding the volume of rotated solid. The method is called the cylindrical shell method, and this isn't as easy to visualize in my opinion. I personally have had difficulty visualizing this. I'm getting better at it, but the other ones seem to make sense. You take this washer, this amount of area, and you slide it up, and all of a sudden you got the entire volume. Okay. What's happening here is imagine a hollow cylinder, like a roll of paper towels, right? The cylinder there, this hollow cylinder. Imagine that's infinitesimally small, thin, all right? And you put that down, and it's the exact height of this cylinder. Then you go just a smidge bigger and slide that on top of the other one, and it goes the right height, and so on and so forth. So basically you get the shell, and then one on top of that, one on top of that, and so it kind of builds the whole thing. And each one of those cylinders is a little bit taller or shorter than the other one. So imagine, so you got a cylinder here that goes up a certain height, and then you got another one that's just a little bit taller that goes right around it. And the next one is just a little bit taller, goes right around it, and so on. And then you just keep on building on. So you have the center one, and then each one builds around it, and eventually you make this whole thing, right? And the reason the cylindrical shell method is even necessary is suppose you have a graph that looks like, I don't know, something like this. And you're rotating it, let's put a vertical line here that we're rotating it around. And then its rotational thing is going to be over here somewhere, right? If I were to do an inside radius and an outside radius for this thing, this is going to be the inside radius. It goes to this curve, and the outside radius goes to the same curve. The same equation makes both sides. So if you can imagine that we're going to get whatever makes the radius happen is going to be the same. And what creates this is this, usually it's a quadratic formula situation where this makes the minus part of it, that makes the plus part of it, that makes it different. But it's really challenging to make that happen, to figure that out. So that's why the cylindrical shell method is even necessary. And how we do it, first two steps are what we did before. Draw the region, shade it, perform the rotation. Do exactly the same stuff. But then we're going to build a cylinder. Okay. For a vertical axis rotation, you need to find the radius and the height in terms of x. For a horizontal, you need to find the radius and height in terms of y. Okay. So before, if we were doing it this way, right, we found this cross section and we went up and down, we did a dy integral. For this one, if we got this, we're going to do a dx integral. And if we do that, we're going to do a dy integral. So we're going to go backwards from the disc or washer method, right? For a vertical axis rotation, the intervals of horizontal extremes. For a horizontal axis, the intervals of the vertical extremes are the original region, so whatever is shaded. So if I'm doing a vertical axis rotation, the region starts at x equals something, ends at x equals something. That's my interval. And if I'm doing this, it's going to be a dy interval. So it's going to be, the region starts at y equals something, y equals something. So that's what we're concerned with. So basically we want to construct this directly from the picture. There's no cross-sectional area happening here. We want to figure out the radius and height in terms of x or y. Again, for vertical it's x, for horizontal it's y, backwards from the other method. And whichever one it is, we want to find the interval for the original region. Okay. We'll construct that integral, and then we'll evaluate that integral. In my opinion, that part's easier than the other one. But the actual construction of it, the visualization of it's the hard part for me on this. So I'm assuming for most people it'll be the hard part. So let's take a look. Find the volume of the solid obtained by rotating about the y-axis, the region bounded by y equals x squared minus 2x cubed and y equals 0. And I gave you like scales on this. What was the x scale?
0.125.
0.125, and the y scale?
0.005.
0.005. It's going to be really tiny. All right, so let's just take a look at this equation. Y equals 0, we all know is the x-axis, right? So basically the curve's going to intersect the x-axis twice, my guess, and it's going to go up above, seeing as I've given us room above. All right. If you didn't know that, you can get some points and figure it out. But if we go y equals x squared minus 2x cubed, and I go to my table, and I'm going up by 0.125, so 0, 0, 0.125, 0.25, 0.375, 0.5. I got back to 0 at 0.5. So starts at 0, goes up a little bit, goes back to 0. All right. So 0, 0 is here. 0.125, 0.011. All right. So 0.005, 0.01, 0.011 would be about here. 0.25 is 0.03125. So 0.005, 0.01, 0.015, 0.02, 0.025, 0.03, and 0.03125, probably about here. And then we got 0.035, so that would be right here. And then we're back to 0. So it kind of climbs up and then it zips right back down. Okay, if I'm trying to draw this, I'm going to do that. The purpose of the graph is not to get a beautiful graph, it's to get an idea of what's happening so we can deal with it. Right? And then y equals 0, of course, is this. And again, I only want to deal with the part that is going to be in our region, so that's not much of it. Again, y equals 0 is a line that goes on forever. This actually continues down, right? So I'm only worried about my region. And then I'm going to shade that region in, like so. All right. We're rotating this around the y-axis. So we're doing this rotation here. That creates the rotation there. So we get the same picture, mirror image around the y-axis. Now, if I'm considering, again, making a decision, should I use the cylindrical shell method, should I use the disc method? Here's the basic way I know to which one to do. Because again, that's one of the problems that we have. We're going to now have two methods to do this. Which one's a better one to use? Right now we're in chapter 6.3, so probably the cylindrical shell method is a better way to do it right now. But there's a reason why. If I draw my circles, so if you imagine there's the inner radius and here's the outer radius. All right? The basic question you have to ask yourself that makes cylindrical shell method the best in this case is, does the inside radius and the outside radius go to the same curve? If the answer is yes, always use the cylindrical shell method, the one we're using right now. All right? And once you've established that, if I were to try, because I always try this method first. In my opinion, that one we did in 6.2, that's the easier way of doing it. Really. I mean, it's much more sensible. It seems to make sense. You take this area and you raise it up, and then all of a sudden you got the whole volume. Right? The cylindrical shell method of putting a cylinder, then putting a slightly bigger cylinder on the top, and bigger and bigger and bigger on top, just doesn't make as much sense to most people. All right? But if the inner radius and outer radius are going to the same curve, you got to use the shell method. No way around it. So here's how the shell method works. So once we've established we're going to use the shell method, we're going to draw our cylinder. It doesn't matter where you draw it, but draw it within the figure somewhere. So you can take a look at it. There's my shell. And again, just imagine the next shell is just slightly bigger than that. It's going to be slightly higher. The height changes, right? Next one's a little bit bigger, a little higher, a little bigger, a little higher, and so on up to here. And then a little bigger, a little lower, a little bigger, a little lower. And each time, each one of these shells is sitting on top of the other shell. And when you put all these cylinders together, you create this whole shape. Right? It's like one's down and then you create a skin for that, and it attaches right to it, the outside, and the next one goes to the outside and so on. So it kind of builds itself out like that. Right? The radius and the height are the two things we care about. When I'm doing a vertical axis rotation, when I'm doing one that's like this, if I was doing the washer method, I'd want everything about y. When I'm doing the cylindrical shell method, I want everything about x. It's backwards, it's the other one. So I need the radius in terms of x and the height in terms of x. Looking at this picture, the radius goes from the y-axis to the curve horizontally, so the radius is x. The height goes from the x-axis to the curve, that equals y. Okay, which one of those is helpful to us?
R equals X.
R equals x, because we want everything in terms of x, right? So R equals x is already ready to go, but the height is y. We don't want it to be y. We want height to equal something about x, but y equals x squared minus 2x cubed. That's the curve we're going up to, right? So height equals y, but I'm going to go with height equals x squared minus 2x cubed. Okay. As long as we're going around an x-axis or y-axis, radius is going to be x or y, height is going to be x or y. But then whichever one you want, use the equation to get the other one. All right? So that's kind of how you're going to go about doing that. And my region starts at x equals 0 and ends at x equals 0.5. And our volume formula is specifically from A to B, 2 pi RH dx. In this case, we've already established dx is what we want, right? The formula officially on that yellow sheet I gave you says dx or dy, but again, vertical axis rotation is going to be a dx. So I need to know what the radius is, got it. I need to know what the height is, got it. And I need to know what A and B are, got it. So you're finding everything you need to create this integral, then you just create the integral out of it. So the volume ends up being, I'm going to take the 2 pi out, just so it doesn't get in the way. 2 and pi are both numerical values. They're constants. They have no bearing on the actual value of the integral while we're integrating, so get them out of the picture. Lower interval 0.5 to upper interval 0.5. Again, whatever's shaded, where does it start, where does it end? And then we're multiplying the radius, which is x, times the height, x squared minus 2x cubed, which I think we can all do mentally, x cubed minus 2x to the fourth dx. That's how we construct the integral. Then we simply have to integrate. We have to evaluate this integral. Oops. Tell you what. I'm just going to put it up here, but I'll just leave it right there. Extend the page. All right, so x cubed is x to the fourth over 4. 2x to the fourth is going to be minus 2x to the fifth over 5. From 0 to 0.5. And if I put 0.5 in, 0.5 is the same as a half, right? Let's go with a half. So 2 pi. 1/2 to the fourth is 1/16 over 4 is 1/64. 1/2 to the fourth. Dividing that by 4 is the same as 1 over 64. Right? 1/2 to the fifth is 1/32. Times 2 is 1/16. Over 5 is 1/80. It's basic, same idea. That's a 5 instead of a 4, so that's going to be 80 instead of multiplied by 16. And then put 0 in, you get 0 minus 0. So 1/2, 1/2, got them. 0, 0, subtract. You're subtracting 0, so it's not doing anything. Common denominator 64 and 80 would be 320. Yeah, 320. So this is 5 over 320 minus 4 over 320, which makes 2 pi times 1/320th, which makes pi over 160 units cubed. Very tiny. Why is it so tiny? seem reasonable as an answer? That's 0.5. This goes up to 0.035.
Oh, yeah.
Pretty small, right? Again, we use a scale in order to get enough size we can actually see what we're doing, but the actual volumes are going to be really tiny because, again, it's a really small cylinder, or I should say, very small solid figure.